We welcome you here at the Technical Forum at the Group Exhibit Hydrogen and Fuel Cells 2013. Please have a seat and have a free drink. You are invited to listen to the next presentation and ask some questions at the end. Come here and enjoy with us the next presentation by Advent Technology, dealing with the topic Recent Development of Advent Technology High Temperature MEAs by the R&D Manager, Mrs. Nora Gourdoupi.
Good evening to everybody. Before we go through our recent developments on high temperature MEAs, let me give you a quick description of the company. Advent was founded in 2005 by a group of researchers coming from the chemistry department of University of Patras, Greece, and the Institute of Chemical Engineering and High Temperature Chemical Processes. At that time, the team had a deep knowledge on the synthesis of polymers and MEAs for high temperature PEM fuel cells, which was gained through the participation in various national and European projects. A very recent success from the company came this January of 2013, where we had an investment led by Connecticut Innovations. Advent is established in manufacturing in Connecticut while maintaining the R&D activities in Greece. So, what is the product of Advent? Advent is producing the membrane electrode assembly, which is the core part of a PEM fuel cell stack. What is the novelty of this material? The novelty is the polymer material itself. So, Advent is producing not only the final product, but controls all the series of products. So, what we do is that we sell polymer, membrane, and MEA under the trademark Advent TPS. Some characteristics of these products are the low cost, they are durable, stable, ideal for high temperature PEM fuel cells, and best for large-scale manufacturing. So, what we are doing now is that we are scaling up. We are scaling up in Connecticut, and in particular, the polymer, the membrane, and the electrode will be scaled up via subcontracting, while the final step, the MEA lamination process, will be held in Advent US facilities. We anticipate to have a volume capacity on 2014 for Advent high temperature MEAs around 300,000 units per year. So I will go a little bit deeper in the technology. Advent TPS MEA is ideal for high temperature PEM fuel cells. So as such, it has all the characteristics of high temperature MEAs, like the high carbon monoxide tolerance or the no need for humidified gases. But in addition to this, we have some extra advantages, which have to do with a very wide operation window between 150 to 220 degrees C, endurance under differential pressure, minimal degradation under cycling conditions. So our concept is that we have thought to synthesize some aromatic polyethers in order to be sure that we have thermal and chemical stability, and we have incorporated the pyridine rings in order to be sure that we can retain the phosphoric acid that is needed for the proton conduction. So the route we follow is that we first design and synthesize the monomers, then we proceed with the polymerization, and we have many characteristic techniques in order to study either the monomers or the polymers or the MEAs at the end, either in-house or through collaboration with the institutes and other universities who have access to many techniques. So what we do as a last step is that we select some of the best materials and we keep working on them in order to have the best commercial products and the various generation of products. So our first generation Advent TPS material is the one that you see here. So this was an aromatic polyether with one pyridine ring per repeat unit. This polymer was quite good for high temperature PEM fuel cells but we need it to be a little bit higher in terms of doping level and proton conductivity. So for that reason, we have included one more repeat unit here, which has the side chain pyridine ring. So in that way, we have increased the polar units into the main chain. So we have increased the capability to retain the phosphoric acid. As you can see, the doping level is higher and the conductivity as well. But how is the pyridine? How does the pyridine retain this acid? We wanted to see how this happens. So here you can see that the pyridine ring, as expected, is protonated. And this can be seen easily from this 1633 band that arises upon protonation. In order to see how much acid we need in order to full protonate the pyridine rings that we have, we keep increasing the doping level and we keep having some of this spectra. So what we did is that we took the ratio of this band that does not further increase when the protonation is full, and we had that band that does not, that stays steady. So you can see here that at 400 moles % of doping level, we don't have further increase of this band. That means that we are at full protonation level. So that means, in other words, we have 4 molecules of phosphoric acid for the full protonation of one pyridine ring for a first generation Advent TPS material. So if we go to another commercial high temperature membrane, what we have seen is that we need 1 molecule of phosphoric acid per polar ring, or in other words, 2 moles per the repeat unit. So, in order to see how the phosphoric acid is retained in our case, what we did is that we doped an Advent TPS membrane, and then we left it for 190 days at 150 degrees C under pressure. So we show that the doping level was stabilized at very close to the doping level that is needed for the full protonation of the pyridine. We did the same for the other commercial high temperature membrane, and you see that again, this was stabilized at the same, not the same level, at the level that it is needed for that case in order to be protonated. So if we compare this table here, you can see that for the full protonation in our case, we have 4 molecules of acid per repeat unit. The other commercial high temperature membrane has 2. The maximum doping level achieved, okay, for the other high temperature membrane is not easily to say because it's so highly doped that it becomes something like a gel. In our case is that, and the doping level after stabilization, you can see here. So what we can say is that if we compare these 2 membranes, in the case of Advent TPS, the full protonation shows the chemical retention of the phosphoric acid is stronger and higher compared to the other high temperature membrane. So upon membrane doping, we proceed with the preparation of the MEA. So now, currently, we have a batch process, but as I told you before, we are establishing our manufacturing in Connecticut, and we're going to have a roll-to-roll continuous process for the MEA. But so far, what we did is that we have a carbon substrate, a carbon cloth, which might be carbon paper in the near future. We then apply the hydrophobic layer and then the catalyst layer. We have the polymer electrolyte, the sub-gasket, and the hot pressing process in order to have the final MEA. Okay, so this is a typical IV graph of our standard Advent TPS material, where you can see that this actually is the new generation Advent TPS, where we have a higher operating temperature of 180 degrees C, and we can tolerate up to 200% of carbon monoxide, and even higher. This does not mean that this MEA cannot operate even lower if needed, because in some cases, some people need to have lower operating temperature. So here you can see that we can go down to 140, but there the performance is quite low. So a recommended temperature window for this particular MEA is between 160 and 180 degrees C. This is the 4,000 hours continuous operation that we have performed so far with a degradation rate of around 11 microvolts per hour. And here is a thermal cycling test of Advent TPS materials, where we would like to show how the MEA performs under continuous on and off. So the protocol that we have followed is that we increase temperature from room temperature to 100 degrees C, no load, no gases. At 100 degrees C, we apply 0.5 volts and we turn on the gases, and we keep increasing the temperature up to 180 degrees C. We stay there for half an hour, and then we go back the opposite way around. What is interesting to see there is that the performance for 130 cycles keeps steady, while the AC impedance measurements that are not included here show that the ohmic resistance of the polymer material is the same, which means that we don't have any leaching of phosphoric acid. But since we keep optimizing our products and we need to have more than one propositions, what we did is that we have prepared a new cross-linked Advent TPS materials, because we know that there is a need for even higher operating temperature, higher than 180 degrees C, in order for some to tolerate more than 2 or 3 or 4% carbon dioxide. So, in some cases, some people, for example, needed to have some internal methanol, as they call it, systems, where they put the methanol reformer on the anode compartment, which needs to be around 220 degrees C in order for the methanol reformation to take place. So the membrane that is here in between should be steady at this kind of temperature. And this is a concept that many people need it, and actually this is something that we have prepared through the participation of a European project. Another need comes from the electrochemical hydrogen separation mode. Some companies want to purify hydrogen, the hydrogen that comes from exhaust. And this is a way, the higher the temperature, the higher the CO that can be into the hydrogen stream. What we did in order to have the Advent TPS cross-linked is that we have inserted a new monomer which could be further cross-linked during the acid uptake procedure. As you can see here, and there will be a comparison table after that slide, the TG value is higher than the previous Advent TPS product, the thermal stability is higher, the conductivity is higher, and the doping level is again much higher. But when we have inserted this monomer that I have told you, the cross-linkable monomer, into the Advent TPS, we first show that the TG value was decreased at 215 degrees C. Upon doping, we doped the membrane, we then put it in water and we undoped it, and we measure again the TG, and we show that the cross-linking happened during acid penetration, and the TG went up to 280 degrees C. Regarding the conductivity, okay, as I told you before, is 1.4 10 minus 2 Siemens per centimeter at 220 degrees C. These are numbers that came from AC impedance measurements coming from the MEA. Here we have the IV curves of the cross-linked Advent TPS MEA, and you can see that the operating window here is again, okay, we only show here the 180 degrees C, but we can go even lower. This operates at 160 degrees as well, but the window is very wide. You can see that we can go up to 220, and we have proven, okay, it's not that much, but it's the first time that somebody shows continuous operation of high temperature PEM at 210 degrees C, where at 0.2 amps per square centimeter we have 690 millivolts, 680 millivolts, with a degradation rate of 25 microvolts per hour. Okay, the question will come on the materials and the other thing around the stack. It's not only the MEA, but at least this is something that shows that at lower temperatures we are sure that we will have a better longevity over time. And this is something we need to do in the near future. So here you can see the Advent TPS, the standard Advent TPS material that is commercially available right now, and the new cross-linked Advent TPS. So what you can see is that the strength of the, if you compare these two, the strength of the polymer has remained the same, the conductivity has changed, has increased, the operating temperature has increased, and of course, the voltage. What we anticipate is that through the continuous process, the continuous MEA process in Connecticut, we will further increase the performance because we are also having there some developments on the catalyst layer, especially the cathode side of the MEA. So we feel that we will increase the temperature and we will have a much more consistent product. Last, I would like to tell you one or two things about the projects that we are participating. So we have a contract with the European Space Agency in order to, with two other partners, in order to provide a regenerative PEM fuel cell. This is a combination of a PEM water electrolyzer and a high temperature PEM fuel cell stack. This is for telecom satellite applications. Photovoltaic gives the main electricity, but when there is no sun, then you need the electricity to come from the fuel cell stack. This is a concept that wants to replace the batteries. In addition to this project, this year we have been awarded 2 more projects with the fuel cell and hydrogen joint undertaking, which was the continuation of 2 previous projects. And we are also participating in many other national projects which have to do with MEA development or the stack production as well. So this is okay. So thank you very much for your attention. And I'm here to reply to any questions.
Yes, thank you very much, Ms. Gourdoupi. Are there any questions from the audience? Feel free to raise your hand. I come around with the microphone. Yes.
Nora, thank you for the beautiful presentation. I just have one question. In one of the slides, you showed the comparison of the performance, the new...
the standard and the cross-linked.
Exactly. And you showed the cell voltage at 650 and 680. I was just wondering what the performance would be at the same operating temperature for the new MEA. Thank you.
Okay, yes, it is the same. It is 10 millivolts higher.
Does that answer your question? Okay. Any others? Not at the moment. So, Ms. Gourdoupi, where can we find you afterwards if questions come up?
You can visit us at the booth D72.
D72. Can you point into the direction because sometimes it's very confusing?
Yes, it's over there.
Okay. All right.
It's right here.
Yes, you're right. Okay.
Okay.
So thank you very much for your presentation, for being here.
Thank you. Thank you.
And we're starting all over again at 3 o'clock, so in about 10 minutes. Feel free to stay seated or sit down and have a drink, a coffee, whatever. We have ultrasonic systems here. The president is Stuart Erickson, and he'll talk about fuel cell manufacturing using nozzleless ultrasonic spray technology. Stay tuned.